Welcome to our Sigma tutorial on protocol security and privacy for database systems. This tutorial was prepared by 6 researchers who have been working with privacy, security, and database systems for years. The team includes she/her myself from the University of Waterloo, Jenny Regis, and Sean Wang from Northwestern University, Johannes Bader, Chenghong Wang, and Ashwin Macharajahala from Duke University. The success of the database systems have been greatly attributed to the researchers and practitioners in this database community. Today we find database systems everywhere, from personal data clouding to business management in corporations. There are many reasons for the popularity and importance of database systems in managing our data. Its logical data model and declarative queries allow a graceful separations between the logical layer and the physical layer of the systems. In particular, the users and administrator of the system do not have to be database system experts. The system can take care of challenges in multi-user concurrent access, data recovery, and scalability issues. But there is one big problem that modern database systems are not fully ready: security and privacy. As an enormous amount of sensitive person data has been collected and kept in cloud or accessed by untrusted third parties, such as location data, smart home devices, we see many security and privacy problems in the news, and no mention of companies who pay millions of dollars of penalty for their improper collection or sharing of sensitive data. There is a desperate need for an end-to-end system solution for non-experts that can manage the sensitive data without breaking security and privacy. Do we have a way out? A quick answer is yes, we have a way. We have a Hawk. We have a lot of power, strength, and 7 PhDs. This approach seems possible. In particular, the security and privacy community has developed a rich set of techniques in the past. Though they do not address the end-to-end workflow of a query execution, we can hire multiple PhD level specialists to deploy the techniques for a particular setting. This is the approach taken by some big data companies. Unfortunately, not everyone can afford that. In addition, these solutions are usually hard-coded, and hence they cannot be easily transferred to other settings. How about general database system solutions for security and privacy? There has been some, but limited work on building end-to-end systems with the security and privacy guarantees from the database community. But each has its own focus of assurance, either in data privacy or secure query evaluation or query verification. A naive integration of these assurance or techniques may even lead to new privacy attacks. In addition, composing this assurance is a non-monotonic cost model for query optimization. It has a much larger optimization space than traditional database systems. How do we get the best deal is non-trivial. It is possible that we pay a huge performance cost but end up with no end-to-end security and privacy guarantees. Last but not least, solutions developed by experts are not necessarily perfect. For example, many cryptographic techniques developed in the past for secure communications has been broken today. We don't want the same thing to happen to our database systems. Therefore, we must take a principled and systematic approach for developing the next generation of database systems. This system will need to treat security and privacy as first-class citizens in their design. This paradigm shift impacts virtually every aspect of database systems, such as how we can access data to how we prepare query results for the user. Hence, it impacts on many core database challenges such as query optimization, storage management, and database operator algorithms. Hence, in this tutorial, we first focus on the principles for defining and designing security and privacy solutions. Second, the primitives that support these definitions. And third, challenges and approaches for system integration and optimization. We have 3 modules that target each of these focuses. The first module covers defining security and privacy requirements for database systems. This focuses on the background, problem setting, and definition. In particular, we will present common architectures in this emerging landscape, and will identify when and where each will need to incorporate security and privacy techniques. Note that we won't be able to cover all the techniques in detail. Hence, in the second module, we'll focus on a few of these requirements and techniques that include secure multi-party computation, trusted execution environments, and differential privacy, to demonstrate these principles that we brought up in Module 1. We also break Module 2 into 2 parts, 2A and 2B, so that we can take questions and a break in between. Module 1 and Module 2 are intended to give general database researchers an overview of the security and privacy landscape in database systems. The second module also provides essential toolboxes for researchers to integrate security and privacy into their own systems. The third module on system integration and optimization provides case studies. These studies show the opportunities and challenges in building practical trustworthy database systems. This module also provides an overview of cutting-edge research that may be of interest even to experts. Time-wise, we plan to complete the first module and Module 2A roughly by 10:50. Then we will take a break and restart our session by 11. We plan to complete the rest of the module by 12:20. We will take questions in between every module that also include the break and the end of Module 3. Now let's come to our first module, defining security and privacy requirements for database systems, or in short form, SMP requirements. You may ask why we want to start with this topic instead of any classic algorithms or the state of arts. This is because defining SMP is a fundamental question and a key principle for modern cryptography. Unlike heuristic approaches that evaluate the solutions based on their perceived complexity or cleverness, this modern and systematic approach aims to provide rigorous proof that a given solution is secure. In order for us to articulate such a proof, we first need a formal definition that pins down exactly what security means, and why such definitions are useful or important. Second, we also need all the assumptions made by the construction to be stated precisely and explicitly. This is because most proofs rely on currently unproven assumptions about the algorithmic hardness of certain math problems, and are related to the power of adversaries or attackers that may vary among settings. Hence, it is important to have precise assumptions stated for the understanding, validation, and comparisons of different SMP solutions. In particular, many SMP solutions are not run in isolation. They are part of their complex systems. Hence, we like to ensure they can be composed easily without breaking each other's guarantee. Last, it is desired that the methods are not hidden from the adversary, or the guarantees should not be achieved via obscurity. Given the formal definitions and precise assumptions, a proof of SMP solution can give an ironclad guarantee that no attacker will succeed. Note that this approach does not end this age-old battle between attacker and defender, but it does provide a framework that helps shape the odds in the defender's favor. Therefore, we would like to take this probable SMP approach when we design and build practical systems for privacy and security. The definitions of SMP greatly depend on the architectures and settings. We need to answer the following questions. Who are the attackers or the point of failure? Are they the clients or the servers of the database systems, or both? Or what to protect, the input data, the query evaluation, or the query itself? Is it about their contents or their integrity? If we want to achieve these security and privacy goals, where shall we integrate them into, and at which level? In particular, do we offer protection at cell level of the table, or the record level, or the table itself? Do we design primitives at operational level, or query level, or transaction level? These choices affect the final guarantees and also performance optimizations. In this tutorial, we will examine 3 reference architectures. First, the client-server setup, where the data sits on a server owned by a trusted data broker, but the client is untrusted, where we put the devil picture beside it. The second reference architecture considers the case where the sensitive data is federated and there's no trusted central server or data broker. Lastly, the cloud service provider setting. In this setting, both data owner and the client are the same party, but they outsource the data to untrusted cloud for storage and computation. These 3 reference architectures are not meant to be exhaustive, but they provide a canvas for us to illustrate the desired SMP definition and ways to achieve them. Among these reference architectures, the untrusted parties are considered attackers or corrupted parties. In this tutorial, we focus on the static model. That means the set of parties controlled by the adversary is fixed before the protocol begins. Honest parties remain honest throughout, and corrupted parties also remain corrupted. Despite they are all untrusted, there are different levels of trust assumptions for allowed adversarial behavior. We'll cover 2 types of common trust assumptions about the attacker's behavior. The first type is the malicious adversaries. The untrusted or corrupted parties can arbitrarily deviate from the protocol specification according to their instructions. In this way, they can either gain unauthorized access or make changes to private information. Such adversaries are also called active attackers. In general, providing security in presence of malicious attackers is preferred. It ensures that no adversarial attack can succeed, but it usually incurs high performance costs and implementation complexity. Hence, a weaker assumptions made by the adversary is usually considered as well. It is semi-honest adversary model, when the corrupted parties correctly follow the protocol specification. However, the adversary obtains internal states of all corrupted parties, such as the transcript of the message, and they can use them to learn information that should remain private. Semi-honest adversaries are also called honest but curious, and a passive adversary. This is a rather weak adversary model, but a protocol with this level of security does guarantee that there's no unintended data leakage. Protocols with this assumption are more efficient as well. We'll now examine the set of SMP notions and techniques with this semi-honest party assumption, with all these 3 reference architectures. First, we're going to look at client-server setup. In this setup, the client would like to learn something from the data owned by the data owner. For instance, data analysts who are interested in learning population statistics will make queries on their data. It is commonly assumed that the server is a trusted data broker acting on behalf of the data owner. This data broker has the true and plain text data stored and processed on the central server according to a valid computation. In this scenario, the client, such as a data analyst, who will send queries to the server. The server will obtain the query answer and return a private query answer to the client. In this case, the client is the attacker, who would like to infer sensitive information about individuals from the released output. We denote these data privacy requirements. In this setting, if the server returns nothing to the data analyst, no information will be lost to the client. However, the data held by their data broker will become completely useless. There are some prioritization methods applied by private work which uses heuristic approaches such as the identifying data, like medical records, or aggregated statistics, for example, the data released by the US Census, or even in the forms of machine learning models for prediction, where you cannot find any individual records. However, existing work have demonstrated privacy vulnerabilities in all these approaches. Simple anonymization does not protect the sensitive information, as adversary can re-identify individuals based on external sources easily. Only releasing statistics does not work as well. For example, an internal team of the US Census have launched a tech that reconstructs records of address, age, gender, race, and ethnicity for about 46% of the US population using data publicly released under the 2010 decennial census. And then they can link part of this data to public data sets. Hence, it is not easy to guarantee privacy. Last, machine learning models also fail. Numerous studies have demonstrated that one can learn the membership of an individual in the training set that's used for training the model. And the fundamental issue here is summarized as follows. If we release too many statistics with high accuracy, we can reconstruct the database and hence fail the privacy. What is needed in the setting is a solution that allows studies and analysis about the population to take place while offering provable and promising privacy guarantees to individuals. As the query is sent by the data client, who is the attacker, and the query evaluation is run by the trusted data curator, we only need to worry about or provide the data curator a solution that offers strong probable privacy guarantee. The state-of-the-art privacy guarantee is differential privacy, which was proposed in 2006. Its goal is to protect the privacy of individuals in the database while releasing useful output of a valid computation to the untrusted clients. A differential privacy has been deployed in industry such as Google and Apple, and government agencies such as US Census. The reasons for differential privacy has been considered and deployed is because it has a formal privacy definition with clear assumptions. Algorithms that satisfy differential privacy always involve randomness, and they should always come with a proof. This randomness allows us to bound the information leakage, and we are going to see more formal definitions in its properties DP in Module 2. The trade-off for the privacy here is accuracy to the aggregated properties that a client wants to learn. Hence, we'll see most of the systems that support differential privacy has an optimization space between privacy and accuracy, unlike traditional database systems that orient at performance. However, we're going to see how differential privacy can also play a role in optimizing the performance of subsystems in Module 3 as well. We have looked at the cases when we have a trusted data curator, right? However, in practice, data can be federated among many parties. For example, medical records are distributed among different medical centers. And how can a data analyst who is considered untrusted to analyze the union of this federated data? The first solution is to have an honest data broker to take the query from the clients and send the query to the corresponding data owners. And each data owner will run this subquery and return the query answer back to their data broker. And data broker will compile this query answer and send it back to the clients. But what could go wrong with this approach? First, for this to take place, we need a complex legal agreements between these data owners for data sharing. And to answer many of the queries, their private records sometimes have to be sent to their owner's broker instead of sending partial query results. However, this owner's broker may suffer a central point of failure for data breaches and saddles this broker with legal and ethical obligations to uphold data privacy. And there will also be side channel leakage with the communication between the data owner and the broker. In addition, each data owner can also observe network traces and query time to learn about the private inputs of the other parties. Or even answer cardinality, right, can be linked to each other. Lastly, the query output can also leak information about the input data to the client in the same fashion as the centralized setting. Hence, a different trust assumption should be considered here. We call this new set of trust assumptions private data federation. This assumes that none of the parties are trusted. In this private data federation setting, the untrusted client broker can be considered to have the same view. Similar to the client-server setting, we need to prevent the client and the data broker from inferring sensitive information about individuals from the released output. Hence, data privacy is needed again in this case. How about data owners? We assume the data owners here are semi-honest. They will honestly evaluate the query over the federated data, but they're also curious about other data owners' input and aim to infer them their computation, such as by observing encrypted data, intermediate results, or set channel information. To guard from this information leakage, we defined a privacy requirement named computing with confidentiality. It is challenging to achieve this confidentiality, as we can see that no parties in this federated setting are fully trusted. Each has its own intent and capabilities. To overcome this challenge, we need to leverage special technologies to bring trustiness for computing with confidentiality. The first technology is local differential privacy. This local version of differential privacy can be applied when no central trusted data curator exists. Each data owner can perturb their input before sending it over to the data broker. This approach offers computation with confidentiality, as there are no computations involved between different data owners and data brokers. Even if the data broker is computationally unbounded, or if the remaining parties collude, the last data owner's data is still protected with bounded leakage. This, at the same time, ensures data privacy. However, the cost of this strong privacy guarantee is the loss of accuracy in the final query answer returned to the client. The second popular technology we want to talk about here is secure multi-party computation. This approach leverages cryptographic techniques to allow multiple parties to compute a function without revealing the private inputs. This technique has been used by, for example, the Boston Women's Workforce Council in 2017 to identify the wage gap between genders. Meanwhile, the companies who offer the data doesn't have to leak their raw wage information to the others. However, the computation cost of this approach can be very high, especially for complex queries. If we want to achieve this guarantee, additional performance costs needs to be paid. The third technology we want to talk about here is TEE solution. This solution has been developed in the last few years. It places trust in hardwares, for example, TrustZone divided by ARM, SGX divided by Intel. Though these solutions provide better performance, they heavily rely on the security guarantee of the hardwares. If the security guarantee of this hardware fails, we then have to revisit the solutions. Note that all these three approaches offer security guarantees. However, those security guarantees are different, as they place trust assumptions at different parts of the computation. Their security guarantees can also be proven with these assumptions stated explicitly. In this tutorial, we'll dive into MPC and TEE in particular to understand their formal privacy definitions, assumptions, and their limitations. Now let's take a look at the last setting, where data owners' clients outsource their data to an untrusted cloud. All the issues that happen to the federated settings can actually take place here as well, as the servers who store the data and process data are not trusted. They can be a point of failure during data breach. They can also view side channel information to infer about the data stored on the cloud. Hence, all the solutions applied to further settings such as TEE and MPC work here too. However, the key difference is that the client is trusted. It is the same party who owns the data and who queries the data. Hence, more information is allowed to be returned to the client. For instance, if the query is to retrieve all records generated by XI, to prevent the server from knowing that XI's records are retrieved, we can return all the records on database back to the client. This leads to a weaker privacy guarantee than computing with confidentiality, known as private information retrieval. This requirement says that the client can retrieve an item from a server without revealing which item is retrieved. Returning the entire database back to their client naively meets the requirements, but clearly it is not efficient. In fact, this is the only possible protocol that can give the client information theoretical privacy for their query in a single server setting. To address this problem, two approaches have been proposed. The first approach is to make the server computationally bounded. This enables many efficient solutions with a smaller communication cost. The second approach allows multiple non-colluding servers, each have a copy of the database. Again, these requirements have its formal and proper privacy definition. The payoff here is the efficiency and communication cost in retrieving items from the cloud to their clients. A symmetric version of private information retrieval happens in the further setting, known as private function invalidation. It is also considered a special case of multi-party computation that evaluates one party's private data using a private function owned by another party. We won't be able to go through each technique one by one, but this table summarizes the key techniques for semi-honest model. In addition, we'd like to quickly discuss the techniques for the case when parties behave maliciously. In this model, there are additional integrity constraints. The malicious parties can act maliciously and deviate from given protocols, such as apply unauthorized updates to the data or apply incorrect query evaluation. The security and privacy solution aims to detect and defend against such behaviors. General approaches include using authenticated data structure, ADS, such as Merkle tree and blockchains, special MPC technologies such as zero-knowledge proof, and TEE technologies can also be used here to defend such a malicious party. But the performance overheads are significantly higher here than semi-honest attack model. Existing efficient solutions could only provide partial integrity for part of the data or part of the query, and sometimes against just a special type of malicious behavior. Composing of the existing methods for an end-to-end integrity guarantee still remain as an open question. Now we come to the end of this module. In this module, we overview the desired privacy and security requirements in three reference architectures. These privacy and security requirements greatly depend on assumptions made in different settings, and the corresponding approaches also vary. Note that each of the security and privacy guarantee has to pay a cost. Hence, in the following modules, we illustrate both the formal definitions and the trade-off between privacy and other aspects of the systems. Thanks very much for attending the first module. We're happy to take some questions.
Yeah, if the audience have any questions, you can post them in the chat, or you can raise their hands, or you can put them on the Q&A Devolver. Okay. And if you come up with some questions later, you can also post there. We can handle them after the second module. Okay, sounds good.
Hello.
Hello.
Thank you very much. Question that we know the privacy and security is sometimes very different. How to what's the difference between security and privacy?
Okay, that's a very good question. The question is about what's the difference between privacy and security, right? And sometimes people use these two words interchangeably. So that particularly require a very precise definition for these two terms when you use for your systems. For example, in the first module, we elaborate on data privacy and computing confidentiality, right? So for data privacy in particular, or for example, using differential privacy, it protects the sensitive data of individuals, cannot be leaked through the query outputs. And how about computing with confidentiality? It protects the data won't be leaked through the computation process. So for example, if we're using MPC or secure multi-party computation to compute a function, let's say, who has a higher salary, or how many people in this room likes security and privacy, right? The secure multi-party computation techniques ensure that you learn the exact function output without the party that participate in the computation learn about other parties' inputs. But the exact function output does not protect the privacy of the individuals participate in the data. So it's not really a simple, like a one sentence answer for this question. But we would like to propose the principle here is really we would like to have a formal definition for either privacy or security when we use or integrate them into systems. Sometimes they can complement each other. Sometimes they conflict with each other, right? So hope that give you a quick answer. Yeah, if you have more questions, we can also take them on the Q&A or the chat. Okay, we're also the office hour. Yeah, you're welcome. Thanks very much for the question. If no more questions, we're going to move on to the next modules. Hopefully that will also clarify these questions about what is the difference between privacy and security and what kind of techniques can be involved. Okay.
Okay, now let's look at the module 2A, secure multi-party computation and the trusted execution environment. As an overview, both MPC and PEE has the same goal. And the goal is to protect the confidentiality of data while we compute queries on top of it in an untrusted setting. So compared with traditional cryptographic techniques like encryption, here, like the goal is that we want to protect the confidentiality while the data is in the change. And over here, like the attack vectors are also different. So first, of course, we want the protection of the data, and that is we want to, for example, have the data encrypted such that the data and all the intermediate result of the data is always kept private. And also, we want to protect like almost all the side channel well, seems that the sound is. Am I the only one?
Yes, I think
yeah, it cut out for me as well.
Yeah.
Okay, so if it seems that there's no sound, so maybe I can just directly talk about these few slides. So essentially, the problem is that confidentiality is very difficult because there's not really anything that we can trust. For example, many parties does not really have any good view. Okay, so however, like if this is just the case, then it will be the best because then we just need to focus on how to instantiate this trusted third party using different kind of technologies. Okay. Unfortunately, like the trusted party usually also send back some other information in addition to the computation of the outcome of the function, and this is so-called the side channel side information. Okay, and this side information may not always be desired. Such side information can have a different kind of form. For example, it could be a program trace, which is about how the program counter moves depending on the input. It could be data access pattern. For example, it is about how the program fetches the data from the memory depending on the input. It could be something that is more subtle, like the program execution time or even intermediate result size. And all of them is one way or another could leak some information about the input. Some of them could be less harmful than others, but all of them leaks information from in some manner. Okay, and for some of them, we could solve them in a naive way by always just heading to the worst case cost. For example, the program execution time, we could try to make the program run it's always in the worst case time. And for the intermediate result, we could also do something similar, such that the size is always padded to the worst case, so that no information is revealed. However, for others, it could be more subtle, like a program trace and data access patterns. These could be more these are like highly non-trivial, and we need to use advanced techniques to hide them in a better way. So in the following, we are going to first focus on data and trace obliviousness for the data and the program. Okay, let's first take a look at the program trace. Okay, suppose that we, following the previous example, we have X and Y as two input set. X has 3 elements and Y has 3 elements. Okay, and let's say how could we implement a program that actually compute the intersection of these two sets? Well, we can just run a double loop, right? So let's say we can first check, and in this particular case, we just wanted to just check the size of our intersection. So we first initialize the result to 0, and then we do a double loop. Okay, so we can just enumerate all the elements in the set X, and then enumerate all the value in set Y, and if they are equal, we just increment the result by 1, and then we can just break so that we can continue to the next element in X. Okay. And we can see that actually, if there is an intersection, then if the number of elements in the intersection equals to the number of times that there will be a break, and the timing of the break, it reveals like which element in X and Y matches to each other. And as a result, we can see that actually the program counter, when we execute this program, highly depends on the value of X and Y. So this is the program that is not oblivious in its program trace, because the program trace depends on the input. And the second trace is data access trace or data access pattern. This can also be illustrated using a very simple example of binary search. Okay. So we wanted to search the value val between the boundary between S and T. So what we do is that we first calculate the midpoint of the array as the array boundary S and T, and then we want to compare the value and the mem at the middle value. And depending on the result, we are going to either search on the left-hand side and the right-hand side. However, this really depends on the value of mid, and the value of mid depends on S and T. However, if we think about it, the value S and T actually depends on the comparison from the previous recursion. So essentially, like if the value is smaller or equal to, then we are going to go to the left-hand side. Otherwise, we'll go to the right-hand side. So this two argument actually depends on the comparison. So in the end, so what's happening is that this memory of mid actually really depends on the value val, and this is an example where the data access trace actually depends on some private input. So we can see actually this kind of different kind of trace can reveal information in many different kind of manners. And in order for a program to be oblivious, So that is like it doesn't really reveal anything from the trace. We have a formal definition. So in our formal definition, we say that a program is oblivious if for any input I of this program, there is an efficient algorithm S such that the trace when executing this program on top of this input is indistinguishable from the output of this program with this algorithm S with just the information of P. So essentially, this means that whatever revealed by this trace when executing the program on the input can be kind of simulated with some algorithm without the input, but only the program. And if this is the case, then it means that this trace doesn't really contains much information about the input. And the exact definition depends on the trace. For example, the trace can be the program trace, it can be the data access pattern trace, and it can also be any other kind of trace. So now that we know the definition of oblivious algorithms, then we can take a look at some examples. And here we are looking at an example of a more efficient oblivious algorithm for computing the size of the intersection. So in the previous example, we could just not run this break in the program. In that way, if we have two sets, each of size n, then the program is going to run in time n squared. Okay. However, we can actually do better by designing something that runs in time n polylog n. So the way and the program is and the algorithm is not that complicated. Okay. So our first step is just to combine the two sets into one vector z. So this is going to contain the information from both vectors. And after we have this this vector, we are just going to set a value result as 0. And after that, we are going to do a trace independent sorting of the vector z. Okay, after this trace independent sorting of z, we are going to get one set such that if the values are the same, then they are going to be located side by side together. And after that, we just need to do a linear scan of the element in the vector. Okay, and if the neighboring value are the same, then we just need to increment the result by 1. Okay, note that now all the accesses to z are actually deterministic because we're just doing a linear scan. And because of this, this for loop actually does not reveal any information. So we can see that actually the whole algorithm is very cheap. It runs in linear time, except this trace independent sorting. And for this sorting, it could actually be done efficiently in time and polylog n. And one example to do this in a trace independent way is to use this kind of sorting network. And we can see, and every error over here refers to a compare and swap gadget. And after all this number of compare and swap, it can guarantee that all the output is going to be sorted, and regardless of the how the input is ordered. And here, this is just a very simple example on computing the size of the intersection of two sets. And this kind of oblivious algorithms could go very, very complicated. And more recently, this kind of oblivious algorithms can go, for example, on graph-based computation. There are also oblivious algorithms designed for specific data structures. They designed to utilize like specific parallelism, and there are also more recent works on how to design like our oblivious algorithms for such that they can support more efficient sorting. Okay. On the other hand, another way is to design oblivious algorithms that can support arbitrary RAM access. And once we have this kind of tool, we can design oblivious algorithms more efficient, like much easier because anyway, like the current algorithms that we design runs on the RAM model. So if we have a oblivious RAM, then we can just port existing algorithms to this kind of framework. As a recap, assuming we have a trusted third party, then we can come up with a solution for confidentiality computation. So we just need to have a trusted party and then send our information, send our input and the function to the trusted party. The trusted party is going to send back the outcome and also come with this side information or leakage profile. Okay, and then in order to mitigate this leakage, we can use different kind of techniques. And previously, we already discussed how to hide the program trace and the data access trace. Okay, the program execution size and the intermediate result size can be hidden in many other different kind of ways. And actually, I believe in the follow-up modules, we are going to talk about some of them, how to use differential privacy to hide some of them. Okay, and from in the next part, we are going to talk about how to actually instantiate this trusted third party. Our first way to instantiate this trusted third party is to use a cryptographically secure multi-party computation protocol. Multi-party computation is actually a very big topic, and it consists of many different kind of protocols and techniques. And as a way to quickly illustrate the concept, let's first look at a simple protocol. Okay. Suppose that we have 9 parties over here, and each of the party has a number. Okay, and the number is only private to themselves. And the goal of all the parties is to compute the sum of all the integers across all the parties. Okay, and we want to design a protocol like this. Okay, and actually, there's a not too complicated solution for this problem. Okay, so the idea is that we could first ask one of the first party to randomly pick a random integer from a very large domain, let's say R. Okay, and then the first party can just send R plus X1 to the second party. Okay, because R is random and very large, R plus X1 is almost uniformly distributed. So it almost does not reveal anything about X1. Okay, and then the second party can accumulate its own input to R plus X1. So the second party is going to send R plus X1 plus X2 to the third party. And the third party is going to do something similar and accumulates its own input to this number, and so on, and so on, and so on. And finally, X9 is going to send R plus sum of all the integers to the first party. And at that point, the first party can subtract R and get the sum of X9. Okay. Well, so the first question is why this protocol is secure. Okay. Well, this protocol is secure because this random value R is large enough. So so R plus any number is going to be statistically indistinguishable from a uniformly distributed number. And the recap remember compared with our previous definition of trusted party, we can actually show that this protocol that is executed among all the parties is as secure as all the parties sending their own input to the trusted party. This is in line. It is in line with the definition previously in terms of the trusted party. Okay. However, this protocol is not exactly as secure as we would hope for. So why that's the case? So let's think about the protocol and see why this protocol could be insecure in some cases. Okay. Well, so the protocol is not going to be secure. Let's say, for example, if the first party and the third party collude, and in this case, so the first party send R plus X1, and the third party gets the value R plus X1 plus X2 from the second party. So if the first party and the third party collude, then they can essentially just subtract the value R plus X1 plus X2 and R plus X1 and get X2 out of it. Okay, so we can see that as long as if any of the two parties in this protocol collude, then they will learn some information about a subset of the party's input, and this is obviously not a very not a very good outcome. Okay, and secondly, this protocol could also be broken if, let's say, the first party instead of sending 0, instead of sending R, it can send a 0. And in that case, there's no random padding to protect the privacy of the protocol. Or if any of the party in the middle could, instead of sending the value, it could just send some 0, so that the outcome of the computation is incorrect. Okay, so we can see that actually, although the protocol is secure from some assumption, it may not be secure on the other assumption. So this means that actually, in general, for many multi-party computation protocols, it's very important to understand what is the security model that we are working with. And there are many different kind of classifications depending on the security models. Okay, for example, the first question that we want to ask is how many parties could collude? Okay, and in this case, the popular classifications involves, for example, honest majority and dishonest majority. Honest majority means that out of all the parties, we assume that the majority of the parties are honest and they are not going to collude with each other. Okay, and if there's a dishonest majority, it means that majority of the parties will collude with each other, which is a much harder case. Okay, and the second question we want to ask is about the capabilities of the parties that are not honest. Okay, so let's say if we want to know whether these like corrupted parties are semi-honest or malicious. Semi-honest means that these corrupted parties will still follow the protocol, but they are just going to try to collude and learn extra information from the protocol. Okay, for example, in the previous protocol, the third party and the first party learning the information of X2 doesn't really require them to deviate from the protocol. So the protocol, if these two collude, they just need to, a semi-honest adversary will be able to learn X2. And then the second the notion is called malicious. In the setting of malicious adversaries, the corrupted parties can do arbitrary activities as long as they think that they are viable. Okay, and in particular, for example, if some party actually changes their input, changes the message to something else, let's say 0, then that's a malicious behavior. And the next question we often want to ask is how many parties are guaranteed to obtain the output. Okay, so here we have all different kind of concepts. For example, security with a board, which means that the adversaries may decide what are the parties who may get the output. And the fairness is also fairness and guaranteed output deliveries are also related concepts. In terms of the formal definition of secure multi-party computation protocols, it also uses the key idea of modeling as a trusted party and also having some kind of a simulation involving the definition. So essentially, so we can view that we have two worlds. Okay, so in the real world, the two parties are going to execute an MPC protocol between the parties, and in the ideal world, the party is going to use a trusted third party. This is what we introduced at the very beginning of this module. Okay, so the security of the MPC says that if there's any adversary that runs in the real world, there exists a corresponding simulation or simulator adversary S, such that from the rest part of the world, these two, the view of these two adversaries are indistinguishable. Okay. So the implication of this kind of definition is that anything that the adversary can be done or could have learned in the real world could also be done or have been learned in the ideal world. And in the ideal world, the adversary cannot really do anything beyond just send the data to the trusted party and get back the outcome and also potentially some leakage profile. So this also means that the MPC protocol actually satisfies this kind of trusted party paradigm. So common building blocks of secure computation protocols there are many different kind of common building blocks to construct efficient secure computation protocols. The basic building blocks include, for example, the Gabor circuit, the oblivious transfer, Beaver triple, and secret sharing. This can be used to build many different kind of protocols in the two-party and multi-party setting. More recent and more complicated tools include, for example, private set intersection, function secret sharing, RAM-based secret computation. They are specialized in certain functionality, but they can be much efficient than just using basic building blocks to build certain functionalities. There are also similar building blocks that could be helpful to construct efficient secret computation protocols, including, for example, private information retrieval for the homomorphic encryption and zero knowledge proofs. Okay. So private information retrieval is a protocol where the client wants to retrieve as a particular block out of many blocks from the server. Okay, so the content of all the blocks are public, but the client does not want to reveal which block is being retrieved from the server. So the server only knows that one block is retrieved, but the server does not know which block is retrieved. That's private information retrieval. Fully homomorphic encryption is a special kind of encryption scheme where we can compute, manipulate on the ciphertext such that the underlying plaintext can be computed without decryption. Okay. Zero knowledge proof is also is another cryptographic protocol where we can prove things about the fact about some knowledge without revealing the knowledge. Okay. All of them can be helpful in accelerating and multi-party computation. For example, zero knowledge proofs can be helpful in designing, for example, maliciously secure protocols. Fully homomorphic encryption can be used to reduce the communication overhead of two-party and multi-party computation protocols. While private information retrieval has been very useful to even retrieve some data from a large array of data inside of secure computation. Okay. So because of the time constraint, over here, I can only give a very high-level introduction of secure computation. And more information, there are many other materials, and many of them has been summarized in this very awesome GitHub repo. So I want to just highlight some important key points. Okay. And for let's say if you want to know more about MPC, I think the best source of to learn them is probably through this BIO Winter School, the first one and the fifth one. This two sets of video lectures actually covers a broad set of cryptographic techniques. And the first BIO Winter School is like 10 years ago. So the content has already been very classical, and many of them it has been implemented in many ways. The GitHub repo also contains a list of existing implementations, open source implementations that you can use. I just want to point out here that in order to choose the open source library that you want to use, you should first think about how many parties are there that you want to use MPC on top of it. What's the security model, whether it is semi-honest or malicious, and what kind of program language you want to hook up with, whether it is Rust or it's Java or it's C++. This kind of decision you should could always impact the choice of the library that you want to use.
Okay, so now we're going to talk about trusted execution environments. So this is a second technology with which we can compute over private data. We also call these TEEs, or secure enclaves, and they use specialized hardware to protect the privacy of database operations. So trusted execution environments are broadly defined as a set of hardware and software components providing necessary facilities to support secure applications. Informally, we're delegating our DVMS's confidentiality guarantees for our data to trusted hardware with a supporting software stack, instead of jointly computing amongst mutually distrustful parties in secure multi-party computation. This execution environment runs in parallel to the machine's operating system and hypervisor. We may use this for databases in the Entrusted Cloud, where we outsource our data storage and query evaluation there, or for private data federations. This trusted hardware is initialized at boot time, and its administrative control is isolated from the remote system in which it resides. For the user launching their enclave on the Entrusted Cloud, they don't need any administrative or kernel level access in order to run within the host system. So the confidentiality guarantee of the enclave means that the enclave alone has the key with which to decrypt the database's private data, and then data may only be accessed by the code running within the enclave. So it does this with a web of trust model for provisioning secrets to protect the data and code. So each time we encrypt the data, we use a key that's derived from a root of trust that is a private key etched into the chip for our trusted execution environment at manufacture time. Now, TEEs also guarantee the integrity of their query evaluation. When we send data to an enclave, we are proving that we are sending it to this secure environment and that this environment is exclusively running our code with no additional snoops. We also verify that the initial data it starts with is intact and not tampered with by the host operating system. In addition, TEEs use secure remote communication to communicate with the end user, as well as amongst themselves for distributed secure query processing. So to motivate this here, let's consider a couple of use cases for this technology. So many of us already use secure enclaves in our workflows. For example, programmable enclaves are used in smartphones to authenticate fingerprints and other biometrics. This makes it so that the system software, including the kernel, if it is compromised, can't be used to falsely authenticate by unlocking the phone or authorizing purchases. And these systems can become quite sophisticated. So for example, Apple manufactures one for its devices that with a system on chip, and it has a fully programmable system, including a boot ROM to establish this root of trust, an AES engine for efficient and secure cryptographic operations, Apple's true random number generator, and a section of protected memory. But more importantly, for us as database researchers, enclaves are seeing use for computing on an untrusted platform such as the cloud. Here, we want to delegate our storage and query workloads to an untrusted third party, such as AWS or Microsoft Azure. But we don't want to disclose our private records to the cloud vendor. Shown below is an example of an overview of how Microsoft SQL Server uses the Azure Confidential Cloud Computing Platform in its query evaluation. So you can see here that from the user's perspective, they submit a plain text query, and the API remains roughly the same as it was before. But now the SQL client driver will encrypt the query and send it as ciphertext over to the engine, where the enclave alone has the ability to decrypt the ciphertext and also decrypt the input data, run the query, and produce the results and send them back to the user, where their client driver will decrypt the answer and return to the client. So here, we're really saying that the system has delegated its query processing to this secure enclave, and this protects the database from unauthorized users, including DBAs, cloud admins, and computer admins on the site to which we're delegating. These individuals may have access to the hosting machine, but not to some or all of the data that we are storing. Under the hood, SQL Server is using Intel SGX for this always encrypted feature. So now these trusted execution environments are moving into the enterprise. As this happens, service providers need a solution that protects private records from data breaches and offers regulatory compliance in some contexts. There are numerous initiatives on this front, ranging from commercial products that have widespread adoption, such as Intel SGX, to open source, more experimental enclaves, like the Keystone Enclave project. And this one is based on the RISC-V architecture. There's also low-powered offerings like the ARM Trust Zone and the aforementioned Apple Enclave. So there's a lot of room in here for research in the DB communities at multiple levels of the stack. So as we will see shortly, these enclaves are not able to scale to running a whole application like a DBMS in one of them, owing to limitations in memory size and computing power. So we typically partition our application logic into trusted and untrusted domains and use the enclave for the former, as shown in this slide. Here, the DBMS runs its private code and encrypts its data in this trusted space to which the host system does not have access. Now, an enclave still may access data on the host system if the user calling the enclave code has permissions to do so. But determining what parts of the DBMS must be implemented in enclave is an important part of this design process. Figuring out when are we touching this data, and what other information are we not willing to leak to the cloud provider, such as perhaps the contents of our query or details of how we run them. At a high level, the enclave is offering the programmer two functionalities. First, we load the data and code in order to launch an enclave. This creates an enclave instance with a unique identifier and a proof or signature verifying that the secure instance has launched with the given code that we put forth, as well as the initial data that we provided to it. And that it's running on this one particular TE or chips. We also leverage features of the hardware itself when we're signing it. The second thing it offers is when we execute, when we invoke a function or a program. And here we call the enclave with its unique identifier and we provide inputs to the program. It produces the output, and it also provides the user with a proof that demonstrates cryptographically that our output was derived from the input program and the initial stored data. So that's how we uphold our integrity guarantee. In addition, though, and this is something where our applications can get challenging, is that TEs are vulnerable to side channel leakage. So we touched on this briefly earlier in the previous section, but recall that an adversary can passively observe IOs in and out of the enclave, network transmissions, runtime, and other characteristics of the query's evaluation, and deduce unauthorized information about the private data or query. So we can't simply port existing DBMS code to an enclave without first hardening it to this class of attacks by making our code's execution data independent. So that's that oblivious feature that we were hearing about in the previous section. So making code fully oblivious is incredibly expensive in terms of performance. Like, we're talking multiple orders of magnitude slowdown if we want to make it so that our database execution truly leaks no information, because effectively we're running in worst case time. So, and that's what we're doing with secure multi-party computation. So we have to make informed trade-offs between full oblivious and running standard code in the enclave, depending upon what types of information we're willing to leak from our DBMS. So the key features that we're getting here are, first, confidentiality for both our code and data. So here we want to protect the confidentiality of private data with an end-to-end approach. So you can think of this as almost like running your DBMS within a virtual machine, albeit a very small one. The data is encrypted at rest, and the enclave alone has the key with which to decrypt it. Recall that the key is based on this root of trust established by the TEE using a private key etched into the chip. Similarly, the code may remain unknown to the host OS and to any observers, because we can input it in an encrypted form to the TE at lunchtime. Once we create an enclave, the code and the data remain sealed in it. They're not accessible by the rest of the system. Hence, the hypervisor and the OS still can't read them. Second, a user needs remote access to the TE, and they do so by setting up an encrypted communication channel between the enclave and themselves. So here again, the TE has to prove that it is legitimately this piece of hardware, and it has to establish this secure channel between the user and itself. So in addition to connecting with the client or the user, the enclave can also initialize and maintain a secure and verified connection with other enclaves for distributed or parallel query processing. With this, we can maintain our guarantees even when our workload spans multiple machines. So our last main guarantee here is that the enclave will have integrity for the data and the code it runs. It also guarantees that the data has not been altered when we page it in from disk. And to do this, the enclave uses measurements to prove to the user that it is running the correct code and that that code is running on the prescribed hardware, and that the data is what we expect it to be. So when we do this in a distributed setting, we're using a similar proof algorithm. Okay, so how do we make this happen? What are the building blocks that we need here? So the first one, in order to do this initialization and launch process for our enclave instance, is remote attestation. So here, we want to verify that we are running on this enclave on this untrusted host. So this is how we provision our enclave. And we generate a set of keys and do a handshake with the user, and with at least in the case of Intel SGX, with Intel, in order to verify that the code, the hardware keys, and the data are as the user expects. And it does so with this unforgeable signature for the enclave, so you can't forge it. The enclave usually communicates with the user and or the OEM vendor for this process, and the enclave must pass attestation before it can start to run the code. So we had to prove that we are running in the enclave with only the code that we expected and with the data that we need. So second, we have this protected, our second big ingredient is we have this protected memory region for the enclave's data. In Intel SGX, this is called the encrypted page cache. And this is where we can decrypt the contents of the private pages in a way such that the host OS can't read them. The Unfortunately, these page caches tend to be small. And we're talking about SGX because this is the most common one, and it's on about 128 megabytes. But its actual working space can be much smaller. And we'll talk about that more in a moment. So third, these systems come with a set of instruction set extensions. And with those, we can create, enter, and exit the enclave. We also invoke these instructions when we're verifying that we're running on trusted hardware for remote attestation, and when we're setting up trusted encrypted channels with the end user or their enclaves. When we're building a DBMS over TEEs, we need to integrate these system calls into the private sections of our application logic. Okay, so with these building blocks, what are some of the design decisions we have to make when we're building this on a trusted execution environment? So if we're building a DBMS. So the first big thing we have to do is we have to define the security guarantees for the system. So in this process, we need to think about our threat models. So we have to say, even though we know that the TE will protect against malicious actors, even on the host operating system, it still remains vulnerable to all these side channel attacks. So you have to spell out exactly what we're protecting and to what extent, like how strong our adversary is. We also need to describe who is permitted to learn what about the data, because that will inform how we protect the side channels like I/O, memory access patterns, and network transmissions. And then we also have to think about how are we going to manage our IOs, our inputs and outputs. So recall that Intel SGX has about 128 megabytes of memory, but once you've loaded up your trusted code base, the code that you're going to run in the supporting libraries, effectively you have about 90 megabytes to work with at a shot. And so we need to partition the DBMS's facilities into small enclave-sized pieces, and that we have to use the same principles when we're paging data into and out of the DBMS. So one useful way to think about this is by starting about it in terms of query execution. What can an attacker learn? By observing the runtime of the query, cardinality of the intermediate results, by looking at when are we paging things into and out of the EPC or our protected memory. But that's not all, because we have to think about this in terms of the larger systems. We have to say, well, is information being leaked by logging if we're doing logging for recovery? What about if we want to do index lookups? Does that reveal certain things about the underlying data, especially if the adversary knows the query that we're running? Things like managing the buffer pool and so on. So we have to take a more holistic view to our database's design when we're thinking about this in the context of TEEs. So our threat model will also, of course, inform what modules in the DBMS must be performed in the enclave. So we have to think both about what subsets of the code need to be run securely. And we also have to think about how are we going to bring data in and out of the enclave in a way that doesn't inadvertently reveal information about the data. So if we're doing things like point lookups and the adversary can see exactly which pages we're bringing in every time, then this is bad. This can leak information about like how many users, like if we're looking at a list of users for a student enrollment system, then we could say, well, now we see that user ID X is enrolled in X classes if we look at how many pages we're bringing in from memory. There's a few common pitfalls that we might encounter while doing this. And this list is not exhaustive. So the first thing is IOs. In a disk-based DBMS, serializing data into and out of the enclave is expensive. And we have a very similar performance pitfall here, where when we partition our data into a format that offers efficient lookups, we have to weigh this against the cost of serializing the data, bringing it in, bringing it out. We don't want to do that repeatedly if we don't have to. But at the same time, we don't want to leak unauthorized information by doing a lot of very specific lookups. And there are some solutions like there's an oblivious RAM for TEs called Zero Trace that can help with this, which brings us down from having to do like an exhaustive scan over the data when we're looking up specific values. We don't want to leak information to, say, a polylogarithmic runtime. But we may benefit from novel data structures here for indexing and lookups. And there's been some preliminary work on this with OblivDB. A second challenge here is that there's really no systematic way to partition a program's native and enclave code to make really strong guarantees. We're basically doing this by hand right now. So when we do this, we have to verify the entire query lifecycle to identify potential flaws in our workload. And this can be really tricky when we have many moving parts together, like logging and index maintenance, transaction or concurrency control, and so on, right? Also, this is kind of an aside, there are some interesting privacy performance trade-offs that we can make when we're designing a DBMS in this setting, meaning that sometimes we may strategically leak some information in exchange for faster query runtimes. For example, we can make our queries run faster if we reveal information about our query results as we go along, such as intermediate result sizes. Or if we're in a distributed setting, we might choose to use non-oblivious shuffle algorithms for things like joining and aggregates. But on the other hand, quantifying the impact or security and privacy loss associated with these design choices is something that we don't really know how to do yet. We can do it in the context of differential privacy, but in the general case, it's much harder. And it's not clear that there even exists a solution for understanding the security implications of these privacy performance trade-offs. So here's a few example questions that we could use when we're designing a DBMS for TEs. One, we can ask, are the queries themselves private? So is the host OS allowed to learn what queries we're running? We can for is something that we don't really know how to do yet. We can do it in the context of differential privacy, but in the general case, it's much harder. And it's not clear that there even exists a solution for understanding the security implications of these privacy performance trade-offs. So here's a few example questions that we could use when we're designing a DBMS for TEs. One, we can ask, are the queries themselves private? So is the host OS allowed to learn what queries we're running? We can again ask about whether we should protect the cardinalities of intermediate results. So here you can see if we're fully oblivious, then the intermediate result cardinalities can really blow up fast because we have to effectively run in worst case. So you can see here just with a simple join that it has an query runtimes. For example, we can make our queries run faster if we reveal information about our query that it has an output size that's equal to the Cartesian product of the input size. And that's clearly not going to scale over a set of joins, right? So another question is, how do we make swapping data in and out of the protected memory data independent? How do we not inadvertently leak information when we're paging in data from disk? And there's a lot of design room here, in my opinion, for access path selection. So thinking like we may find more ways to bring data in, that doesn't mean we have to scan the whole relation every time. So another thing that just to touch on briefly is that TEs have vulnerabilities. So like all systems, they're susceptible to cycles of finding new attacks, catching them, and then beginning the process again. The side channel problem really can come up because it means that people have been spending a lot of time in the security community analyzing this problem. So here, attackers may try to reverse engineer data access patterns by forcing the enclave to swap in and out of memory. They may also try to exploit speculative execution, like SGX's foreshadow, to extract the enclave secrets, i.e. its decryption keys. But the thing that makes this problematic is that sometimes we can't patch it with software. Sometimes, like for example, with Foreshadow, we have to patch this in physical hardware, and that means that updating it can be very costly and time intensive. But so even though we may not have entirely figured out this hybrid software's hardware system security yet, this is still a valuable platform with which to do research, and it will continue to get better with time. So briefly, there's been a fair amount of work on this topic of DBMSs on TEs. And this really started with Opaque in 2017. And here, this was for select project join aggregate queries, and it supports only read-only OLAP workloads. OblibDB extended this line of work. They added a simple oblivious index structure, and they started to support writes. And there's been work also with EnclaveDB, which is more of a full stack solution. So they offer stronger performance on transactional workloads and built-in checks for the integrity and freshness of recovery logs and of the DB itself. StealthDB is also an interesting work because they sit atop of Postgres, so they really tried to implement this in the context of an existing system, and they investigate a few security models and design trade-offs for performance. But the main thing to bear in mind here is that DBMSs on these trust execution environments have a wide range of decision space options, and in terms of both the workloads they serve and the level of confidentiality and integrity guarantees they can offer. And there may still be fertile ground here for additional research for workloads like HTAP and improving the performance of current systems. So to briefly summarize, in contrast to secure multi-party computation, the TEs are much more efficient for performance. And they also naturally parallelize in a way that secure multi-party computation cannot, because they compute locally instead of evaluating these garbled circuits by passing encrypted messages around the network. So then with MPC, the network can become the bottleneck, and TEs will parallelize more nicely. Now, the cons are that you have vendor lock-in. So for example, with Intel SGX, if you want to do remote attestation, you have to go through Intel. So that means you have to trust Intel. They're also vulnerable to side channel leakage. And that sometimes these security guarantees can be brittle because hardware fixes are slow to roll out. And with that, I thank you.
Now, okay, I think that's the end of this module. If you have a question, feel free to leave any comment on the questions over here. Let me check if there's any question on Hoover. Yeah, I think there's not really any questions. So so Ke made a comment over here that on page 34 there's the example has a oblivious query plan of big ON cost. Thanks. I will check with Jenny, and we will make a note on the slides when we put it online. Thanks. Are we is there a break afterwards, or?
I think we can come back at 11. We can take a few minutes break, and then we can play the video again.
Sounds good. Sounds
Okay.
good. Let's have a bio break.
At 11.
Yep.
Okay. Hello everyone, my name is Chen Hong Wang. Welcome to the tutorial. This module is about differential privacy. Throughout this module, you may expect the following contents: the desiderata for defining privacy, the basic definition, technical knowledge about differential privacy, the existing solutions that integrate differential privacy into database design, as well as some open challenges. Let's start with a well-known privacy breach example for Massachusetts governor. So assume the hospital publishes certain medical data where they anonymize important identification information, such as the name and the social security numbers. However, attackers can still infer sensitive information by combining the medical data with another public table, which is the voter list. Then, according to some crazy identifiers, the attackers can identify the record in the medical data that belongs to the Massachusetts governor. So the crazy identifiers are pieces of information that are not themselves unique identifiers, but are sufficiently well correlated with an entity that they can be combined with other crazy identifiers to create a unique identifier. So for example, you may not be able to identify an individual by using only the zip code, the DOB, or the gender information. But by combining these three attributes together, almost 90% of US populations can be uniquely identified. So we then claim these three attributes are crazy identifiers. And here's one solution for this, which is called k-anonymity, which could avoid linkage attacks. The k-anonymity works as follows. If every row corresponds to one individual, then every row should look like other k-1 rows based on the crazy identifier. Here's an example about for anonymity. And if we consider the zip code, age, and nationality are crazy identifiers, then each row should look similar to other three rows with the crazy identifier attributes. However, this k-anonymity setting may have issues when the adversary has some background knowledge. For example, assuming the adversary knows that Emiko is a 25-year-old Japanese who currently lives in zip code 13053. And based on this information, the adversary learns that Emiko's information is contained in the first four tuples of the given table. Without additional information, the adversary is not sure whether Emiko caught a cancer or has a heart disease. However, it is well known that Japanese has an extremely low incidence to have a heart disease, and therefore, the adversary can conclude with nearly certain that Emiko has a cancer. And this is a type of inference attack that utilizes background knowledge. There are many types of attacks that using background knowledges. There are attacks against Netflix data, against search log, and against social network. Therefore, the first desiderata for privacy definition is to resilient from background knowledge. That is, a privacy mechanism must be able to protect individuals' privacy from attackers who may access the background knowledge. The second problem of privacy is that many organizations may think their data are private because they perturbate the data and make some parameters of the perturbation secret. However, this is a very strong assumption. And in a general privacy definitions, we should assume that the attackers could somehow obtain those secrets and they are well known about how the algorithms works. So the second desiderata for privacy definition is to achieve privacy without obscurity, which means that attacker must be assumed to know the algorithm as well as all the parameters used to achieve that algorithm. The third major problem of privacy is the post-processing. Let's take a look at this example where it releases an aggregated statistic for a group of people according to two attributes, the age range and the race. So to achieve the k-anonymity, for any counts that are less than k, they are suppressed without revealing the exact number. Okay. However, by doing some simple math, the suppressed value can be computed, and this leads to a privacy breach. So the third desiderata for defining privacy is the post-processing property, which means post-processing of the output of privacy mechanism must not change the privacy guarantee. The fourth problem is multiple release problem. For instance, if two hospitals both uses k-anonymity to release their own data, one uses 4 anonymity, another uses 6 anonymity. Now, let's assume Alice visited both hospitals and she is 28. Can you deduce Alice's medical condition? And the answer is yes. And this implies that the 4 anonymity plus 6 anonymity does not give you another k anonymity. Right? So that is a problem about the multiple release. And so here we need to introduce an important theorem, which is the database reconstruction theorem, where informally, if too many statistics are released too accurately, the vast majority of the records in the hidden database can be reconstructed. And the attack that finds the database D that best matches with released statistic over a hidden database is called the reconstruction attack, which has been successfully demonstrated by US Census in 2019. So in order to ensure the utility, a statistical database must leak some information about each individual. So we can only hope to bound this amount of disclosure, but we cannot eliminate them. Therefore, according to the reconstruction theorem, there is a limit on number of queries that can be answered. So the last desiderata for defining a privacy is the composition over multiple release, which allow a graceful degradation of the privacy with multiple invocations on the same data. Now let's take a look at some basic concepts for differential privacy. In general, differential privacy is not an algorithm or a property of the algorithm's output. It is a property of the algorithm itself. So let's keep this in our mind and we will start our discussion. Let's start with an illustrative example, and we think about the setting where a trusted data curator collects data from data subjects. Sample curator can be a hospital, and the data subjects can be a patient for that hospital. In the meantime, there is a group of external analysts who may wish to make some analysis over the data managed by the data curator. In a default way, the analyst can ask the data curator to evaluate a certain algorithm over their collected data and release the output back to them. However, the data subjects may concern about their privacy. For example, the Bob is a patient of the hospital, and he may want to know that could releasing the result of the algorithm A reveal his risk of her disease? And could this lead to an increase of his insurance premium? And to solve this, we need to formulate the concept of the privacy. Now we start with our first attempt to define the privacy. And if we think a mechanism is private, if an attacker cannot learn much about an individual beyond what they can already know. And apparently, this is not a good definition, as the learning principles of nature should not be considered as a privacy breach. So we start with a second attempt, and we consider an algorithm. So if the information that we can learn about an individual from this algorithm is similar to what we can be learned from an opt-out word, where the individual is absent from the input data. And in that case, we may say that the mechanism is private, or this is a privacy-preserving mechanism. Okay? And then, if we formally define this, we will introduce a new term. It's called differential privacy. Then we consider a mechanism A satisfies differential privacy if for any pairs of inputs that differ in one row, and for any possible output, the adversary should not be able to distinguish between that pair of inputs based on the outputs. And so why we consider pairs of databases that differ in one row? Because this simulates the presence or absence of a single individual or records, which means that it can capture the membership of the records. Right? And usually we call such a pair of databases that differ by only one record as the neighboring databases. Now, the second question is why we consider the all pairs of inputs, or the all possible pairs of the neighboring databases. So as the privacy guarantee should hold no matter what other records are. And that's why we should consider all pairs of the neighboring databases. And what is the epsilon stands for? The epsilon here is the privacy parameter. It controls the degree to which the neighboring databases can be distinguished. And smaller epsilon means the advance to distinguish between neighboring databases is relatively low, which implies a better privacy. And usually better privacy means a worse utility, and this will be discussed in a later section. Now let's take a look at a typical approach that achieves epsilon differential privacy, which is called Laplace mechanism. So the analyst can make some query request to the curator who manages a private database. And such query can be a counting query, which aggregates some results. And the aggregate computes the query over the private data. However, instead of releasing the exact query answer, the curator distorts the results with some differential with Laplace noise and reveal the noisy answer back to the analyst. So one major question is, how much noise should be added for privacy? And the general question is, the noise added should be proportional to the global sensitivity. So, and the global sensitivity is defined as, for a query, is defined as the maximum output change for any pairs of neighboring datasets. In adding Laplace noise proportional to the global sensitivity to the true query answer satisfies differential privacy. Okay, let's take some examples to learn more about the query sensitivities. And the first query example is a counting query. For instance, the query that counts how many people having flu in the given relation here. And knowing that adding or removing one record from the database D, the counting query outputs only changes at most one record. So therefore, the global sensitivity is 1. And to answer this query, the curator first computes the true counts, which is 2, and adds Laplace noise proportional to 1. Another example is the summation query. And for instance, the query that sums the total usage of drug X. And if we assume that all values for drug X usage is a real value within range A and B, then we know that the global sensitivity is equal to the maximum possible value of X, which is B. And similarly, to use Laplace mechanism, the noise should be added proportional to B. In general, Laplace mechanism works for any function that returns a real number. To learn about the utility, we formulate query error as the expectation of the square root difference between the true and the noisy query answer. Then we can learn that the error is actually the variance of the Laplace noise added to the true answer, which equals to 2 times square of the global sensitivity divided by the square of the epsilon. And it's not hard to see that a large global sensitivity or a smaller epsilon implies higher error, which is less utility. And recall a statement that we have discussed earlier, a better privacy means a smaller epsilon implies worse utility. Okay. So from here we can conclude there exists an accuracy-privacy trade-off for Laplace mechanism. And actually, Laplace mechanism is not a unique one. There are many differential privacy algorithms, such as exponential mechanisms, randomized response, Gaussian mechanisms, and so on. and each of them gives a different accuracy privacy trade-off. We have learned how to respond queries in a differentially private manner. Now let's talk about how to release multiple differentially private queries and how privacy is composed. The first theorem is sequential composition theorem. And it says that if we apply multiple differentially private mechanisms over the same database, and then the total privacy budget equals to the summation of the privacy budget of each sub-mechanism. In other words, if we release multiple differentially private queries, and then the total privacy cost equals to the summation of the privacy budget that is allocated to each sub-queries. The second theorem is post-processing, and where it states that applying any operations over the output of any differentially private mechanisms does not change the privacy guarantee. And in other words, if we already responded some query in a differentially private manner, and then any post-processing operations over that query answer will not change the privacy parameter. So far, we have talked the basic definitions and concepts of differential privacy, and actually, differential privacy has widely adopted by various real-world use cases. And more importantly, the additional tools and packages that supports DP experts, programmers, and even non-expert users, which is a positive sign. Well, one of the big issues that standard databases cannot handle is privacy. And in the next part, we will introduce integration of differential privacy into DB design. And fortunately, there's actually many works that have already done this in practice. And some nice thing about the system is that they leverage the standard query language in database system, and then you can actually answer a large class of queries whose sensitivity can be automatically analyzed by the system based on a set of rules. So here's a very simple example. And assume if you have a person table containing individual attributes information, such as person ID, gender, family, or geolocation information. And if I just want to ask how many people from North Carolina, we can formulate the query as an execution plan and then analyze the sensitivity or stability of each operator and get an overall sensitivity, which is pretty straightforward. The previous example is pretty straightforward, and most of the systems have already implemented this. However, what if we group by in the end of the query? For example, we would like to count the number of individuals and group by the geolocation information. Based on the given person table, we know that all individuals are from 3 states. Therefore, the group by results will also show that only 3 states have data, which leak the active domain information. There are some existing solutions for this problem. That is, we can specify the group by keys, or we use a predefined partition. For example, when we group by the geolocation, we will use all states rather than the active states. This opens up a new general research problem of designing a private data manipulation language that can handle related subqueries. And apparently, this requires additional specification of privacy budget or accuracy. Another question is, what if multiple tables are stored? As in practice, when you look at a lot of structured data stored in hospitals or in large corporations, you rarely find just a single table. For instance, in addition to the person table, we also maintain a household table. An individual in person table may have a corresponding records in the household record. Similarly, if we follow the same query execution plan as we discussed in previous slides, we can obtain the sensitivity as 1. Since adding or removing one of the rows in the person data, the query output changes at most 1. Now, what if we remove one row from the household table instead of the person table? To analyze this, we rewrite another query plan. We first apply a filter on the household table that filters the rows with geolocation equal to North Carolina. Then apply join with the person table. Afterwards, we get a count. By adding or removing one row in the household table, the filtered results changes by at most 1. But the joint output changes may greater than 1, since one household may have multiple corresponding entries in the person table. As a result, the overall sensitivity will be the maximum joint multiplicity. And according to the analysis, we find out that by removing rows from different tables, we turn out to obtain different sensitivity. And moreover, by removing rows in different tables, the privacy objects are also different. For instance, removing rows in person table preserves the privacy of individual person, but for the household table, the privacy is preserved for a single household. So different works may consider different privacy objects. For instance, PinQ and Flex only consider a single row in the table, while Google DP paper enforces the user-level privacy, where the privacy is preserved for each individual. Private SQL then provides a more complicated private object which is based on a foreign key constraint. For many cases where data are complex, it's pretty common that there exist many different privacy objects. For instance, for graph data, we may have age privacy or node privacy. And in the given example, we may have person privacy and household privacy. To automatically handle this case, in private SQL, the authors propose a semantic privacy notion called policy. It defines one of the relation tables to be the primary object, and then it can leverage the foreign key constraints between the tables to track which tables are also protected, and calculate the sensitivity of query correctly. But the current limitations are the system only considers select foreign key constraints. Let's take a look at how private SQL can be used in our given example. Consider we set policy as person, meaning that person table is the main private object. And given a query that search individuals with age greater than 17, we learn that this query is only applied over the person table, which is the primary private object. And therefore, we can write a query execution plan as follows. We first apply a filter operations over the person table that filters out all rows with age greater than 17, and then we return the retrieved outputs. And knowing that adding or removing one row from the person table, the resulting query will only change by 1. Thus, we obtain the sensitivity on the policy person equal to 1. However, if we think of the policy is set to be household, where the primary private object is changed to the household table, then if we calculate the sensitivity using the same execution plan, then we will obtain a wrong sensitivity, since the query execution plan does not apply over the primary private object, which is the household table. To address this problem, the query needs to be rewritten by a semi-join operator, and the resulting execution plan is as follows. First, a semi-join operator is applied over the person table and the household table, followed by a filter operator that filters out all rows with age greater than 17, and then returns the outputs. And based on the new query execution plan, changing one row in the household table may lead to more than one result affected in the semi-join output. Thus, the sensitivity for semi-join operators equal to the maximum join multiplicity. In addition, as the filter and the search operators have sensitivity bounded to 1, therefore we obtain the overall sensitivity equals to the maximum join multiplicity for semi-join operator. So what else could go wrong here with the multi-relational database? What if the sensitivity of join query is extremely high? And what if the maximum join multiplicity is not public? Fortunately, there are some existing solutions for this. For instance, PinQ uses grouping before join to bound the sensitivity for the join operator. The Google DP paper proposed a contribution bounded approach which manually specifies an upper bound for the join multiplicity. Flex consider using smooth sensitivity, while in private SQL, the authors use truncation with an automatically learned threshold to solve this problem, which offer a more accurate sensitivity calculation approach. The main idea presented in private SQL is to have a truncation operator to bound the maximum multiplicity of the join key. For instance, when computes the semi-join between household table and person table, it first applies a truncation operator to the person table, which restricts the maximum times a record in person table can be joined with the household table. And here we just bound it as a k. And therefore, the sensitivity of the semi-join is then bounded by k. And the following filter operator has a bounded sensitivity equal to 1. In general, we thus obtain an overall sensitivity for the entire query that is k. So as a summary, there are various existing solutions for handling join queries with unbounded multiplicity. For instance, we may utilize the smooth sensitivity, the truncation, sampling, or use the key tracking approach proposed in the private SQL paper. And additionally, there are some open questions as well. For instance, we may be interested in which algorithms to use. Under what circumstance one algorithm is better than the other one. And also, how to physically implement differential privacy into DBMS is also another interesting problem. Some subproblems for this topic includes how to support key tracking in the query plan, and how to efficiently compute tighter sensitivity upper bound for better accuracy. We may also face problems when dealing with multiple queries. And this is also a critical point where the integration of differential privacy with databases may go wrong. For instance, if we issue unlimited number of queries, and according to the composition theorem we have discussed earlier, we know that we either incur unbounded privacy loss or we have to stop query answering for after certain rounds of response, which is not ideal in the real-world implementation. To address this problem, there is some work that proposes the approach to generate a general differential privacy view for answering multiple queries, or catch historical query answers, which is used laterally to respond to future queries. However, there are still some open questions here, like how to ensure consistency between each of the queries, how to allocate privacy budget among different queries, and also how to pick the proper differential privacy algorithms for answering multiple queries. Additionally, there might be some general implementation issues as well. For instance, the first problem is how to handle the side channel attacks, which means that the adversaries may be able to observe answers to their questions, respond time, system decisions to the execution query, or deny it. And in some cases, by observing their execution side channel leakages, the adversary can actually infer some critical information about the original database. The second point is the randomness and floating point issues. The randomness implementations in differential privacy is a big issue. For instance, how we could guarantee that the randomness is honestly generated. So far, we have covered all key aspects of this tutorial, and let's summarize it. We start with the principles for defining privacy, and then learn about the basic concepts for differential privacy. Lastly, we explore the system designs that integrate DP with databases. As per the current design for adopting DP to databases, there are some interesting open questions. The first open question is how to design private data definition and private data manipulation language. More specifically, how to protect the privacy at a correct resolution, how to prevent unsafe and non-private query being executed, and how to provide a better accuracy for complex queries. Secondly, even though there are many existing solutions that integrate DP to database design, there are still some remaining problems, such as how to add the DP on the top of existing database design, and how to re-implement DP components for better utility and performance. So that's all for this tutorial module, and please feel free to ask any questions.
Yeah, we can take a few questions from the audience. You can post a question on chat or.
Hello, thank you, Professor. I have a question that sometimes our database, our data set may be some sequence, such as some time correlated sequence. So how to handle this data set? If we choose to handle it by and at the same private budget, it may be very rigorous. So I just want to know how to handle the data set or database like time correlated database.
Okay, thanks very much for the question. So the question is about how do we handle time correlated data,
yes,
right?
Yes.
So there's multiple ways to go through this. There are actually consistent officially private paper regarding how to handle time series data, but they are not necessarily modeled into the database systems where there's no particular temporal database systems has been built particularly for differential privacy. So I would say this is a very important open question, right? But in order to deal with this question, we're taking the similar approach, first define what does mean by privacy there when we're dealing with temporal correlated data. The definitions could be different for the standard relational database model, right? And secondly, we need to have our algorithms that design for this new privacy definition. And probably some of the existing differential private algorithm for time series data could be adapted here into the system. If you want some of the paper links to the paper, you can post a question in the office hour or the Q&A session. We can link some of the related papers to this topic. Hope that had give you some idea about this question. But this is a really good question and a very important directions for database systems.
Thank you, Professor. And I have another question. If we there is a model that we are not trust for the aggregator, and we use the local differential privacy. Sometimes when in that circumstances that we need to do some matching without knowing the individual location. But if we disturb the data using local differential privacy, the matching result will be very poor. The error will be enlarged. I want to ask how to handle this problem.
Right, this is again very good question. Yeah, so I will just repeat the question for clarification. So the question is it's possible to apply local differential privacy when there's no trusted data curator or data broker. So differential privacy is applied to perturb the records, in this case, location of each individual. But when you are trying to, for example, matching those records, for example, you want to join like two tables and you perturb the join keys, right? And their join results are going to be very bad. And there's a theoretical bound for this approach. You cannot get an accuracy very well for such a join over local DP algorithm apply on the join, where local DP algorithm have been joined on the join key. So I think Shell suppose there's potential solution MPC there, right? So as we mentioned in module 1, it's really a trade-off between trust assumptions and accuracy and performance. So one possible approach which actually proposed in the private work is to build our MPC solutions where you shift the trust curator to the computation, right? where, for instance, you can encrypt the records of the location and aggregate them together, use homomorphic encryptions, right? And then you can get a more accurate answer for the aggregate queries. But the trade-off here is going to be the performance is going to be much more expensive than you just run our local DP algorithms on the location of the of each individual. Right.
Thank you very much.
Okay, yeah, but there is definitely more approaches towards these directions. I think there's a wonderful work that the database community can contribute along this line.
Yeah, actually, in the next section, I believe we'll briefly cover one of the systems that sort of attacks the exact problem. So it's like how to convert the sort of local differential private case into a sort of a more central model where you have the aggregator doing able to this computation and adding the noise afterwards without having to have this trust assumption.
Okay. That's great.
Hi, professors. Thanks for the tutorial. And I have a question about the composition of mechanisms. And I guess it will be a very technical question. So in the standard formulation of compositions, the adversary will give a mechanism and its privacy parameter epsilon, so that the data curator will return the answer, and then the adversary will give the next mechanism with its privacy parameter. Yeah, but in my opinion, the privacy parameter does not have to be explicitly given, because you can derive the parameter from the mechanism itself. For example, if I say my mechanism is adding Laplace noise of global to the magnitude of the global sensitivity, then as a data curator, when receiving the mechanism, I already know it will satisfy epsilon dp for epsilon is equal to 1, right? So I mean, the privacy parameter can be defined as the maximum probability difference between any two neighboring instances. And my question is that under this definition, which means the adversary only gives the mechanism but not the parameter, can we still apply the compositions as in the standard way, which is, for example, if we have two mechanisms which are epsilon 1 private and epsilon 2 private respectively, we can say that their composition is epsilon 1 plus epsilon 2 private. But then in my understanding, for example, let's say the privacy parameters are not given explicitly, but derived by the data curator, for example, from the mechanism itself. Then can we say the composition is still, let's say, Laplace, we give two mechanisms which adds Laplace noise of global sensitivity, and then global sensitivity divided by 2. Then can we say the composition of these two mechanisms satisfies 3 dp, for example? Yeah, thank you. That's my question.
Okay, that's a very good and interesting question. So I think I try to rephrase the question in the following way. If I were describing that a way, is that I have a mechanism and there's noise have been injected into this mechanism, right? Is it possible for us to analyze the privacy loss of this mechanism, right? Rather than from a different way, like I define this algorithm 1 is epsilon 1 dp and algorithm 2 is epsilon 2 dp, and then we apply sequential composition. And the answer is yes. I will give an example for differentially private machine learning algorithms. When we're converting a non-private stochastic gradient descent algorithm to a private version, we really add noise to the gradient. And in order to control the amount of noise that we added, we're going to clip the gradient first, which is kind of control the sensitivity of the gradient, and then you add a noise proportional to that. Right? We rarely claim that this gradient particularly satisfies some differential privacy guarantee, but we use a more advanced composition or moment accountant composition techniques to analyze the overall privacy loss of this this kind of algorithm. So hopefully that kind of answers your question. Yeah, I guess that's it. yes. And yeah, if it's not clear, again, like we can discuss that in the office hour. You can pose a question in our tutorial session on OVA. Yeah, this is a great question. And we hopefully also can apply this kind of advanced composition techniques or this kind of techniques into database systems, which we haven't done that yet. Okay, so yeah. Sounds good. We probably will move on to our last module, which is very exciting. It's about, as Joe has mentioned, it's about integrating all these techniques we have talked about into database systems. Let's look forward to
it. Sorry, Professor.
Yes.
Can I still ask a question about the differential privacy?
Okay. Oh, is it going to be a short question? Probably just
yeah.
Okay.
Thanks to give us such wonderful talk. My question is, in privacy SQL, you mean we need to indicate one primary private relation, right?
Mm-hmm. Yes.
So maybe in some cases there are some more than one primary private relations in the query. So how to deal with such problem, or do you think that is also meaningful?
Yeah, that's a good question. So in private SQL, we define a primary private relation, and all the other relations that are private are from a foreign key constraints with the private relation. But it's still open questions on how do we define or privacy over relation over a schema that have multiple private primary relations. So private SQL does not solve that problem. It's, if you have any idea where you want to talk about it, it's going to be great.
Okay, I see. Thank you. And another very short question is, I did not notice the Google DP previously. Can you post the link of this paper?
I think, yeah, okay, we can post the link there, but you can really quickly do a search Google differential privacy, bounded user contribution. I think those keywords will lead you to that paper or to the code.
Okay, thank you. Thank you.
Okay, sounds good. Let's have our module 3 then. Thanks.
Hi, everybody. My name is Joe Hess-Bader. I am currently a postdoc at Duke, and I'll be presenting module 3 of our tutorial today. And so today I'll be covering system integration and optimization. Okay, so what exactly does that mean, system integration optimization? So there's 3 main parts. Part 1, I'll be looking at DBMS security and privacy, right? So how does security and privacy fit into databases? What are the different techniques that we're going to be using? Why do we even care about these techniques? Second, we'll be looking at state-of-the-art solutions. So there's a lot of great research out there currently, and we'll take a look at what are the great parts that they're using, how they implement these security and privacy techniques into them. And then finally, we're going to look at open challenges. So existing work covers a lot, but there's really exciting work that can come out, and it's fertile ground for future research. So part 1, DBMS security and privacy. So security and privacy, we're going to think about in two different main settings today. First, we're going to look at a client and server setting, and then second, we're looking at an untrusted cloud. Okay, so in a client server setting, we have a data owner who holds all the data. This is all holds the private data, and they're trusted. And then we have an untrusted client who is who's querying this data owner and wants to receive some result. So in this setting, the client is not trusted to see what the private data is, however the data owner is. And so the data owner must decide, how are we going to answer the query such that we are able to accurately answer the query while preventing the client from accessing unauthorized information. Okay. Second, in the untrusted cloud setting, again, we have 2 parties, but in this case, we have an untrusted cloud, which is actually going to be holding on to the information and in charge of processing queries, and then a data owner or client who's actually trusted, right? And so in this setting, the data owner wants to run the query and process it on the cloud, So this is some outside cloud provider without revealing to the cloud what this information is. Okay. So these are two main settings that we're going to look at today. And the idea here is that we want to have a column ahead of time access control policy. And we want our systems to behave sort of like exactly like a standard DBMS from the client's perspective, right? So we want them to be able to just send queries and receive results without managing too much else. Okay, so the idea is, first question you have would be, why can't I just add a password to my database and are using encrypted storage, right? So again, yeah, so we could say like, in this setting, why can't I just sort of encrypt my data and store it on the cloud, and then sort of run this query over the encrypted data. And so the problem here is that when we think about security and privacy, our attack surface is the entire stack. So the entire stack of the database system. And so our data may reside on untrusted cloud servers, and so we sort of need to re-architect our systems with security and privacy at the forefront. Okay, so we can look at if we have a naive DBMS plan on an untrusted cloud, what could go wrong here, right? So in the figure we see the client data owner, and we have this as well as a virtual private cloud or a cloud provider who's untrusted. Okay, and we can say that the cloud provider has an encrypted database where the data owner has previously uploaded records that are encrypted into this database. Okay, and then we say that, the client can then sort of query this encrypted database and receive some results over some SSL layer, and voila, they're able to send the query and receive results without letting the cloud provider know what the information is. However, this is not quite so simple, right? So there's a few things that could go wrong. First, storage. So if the cloud provider, sort of encrypts the data themselves, then that means that they're able to unencrypt it as well, right? And so you could have governments sending a national security letter or something that can compel a service provider to decrypt this data and provide it to them. Thus, sort of allowing somebody else to access this private information. Second, in terms of query processing, an insider threat or somebody who's has taken over or able to compromise one of the cloud provider is able to see sort of data-dependent query traces and result sizes potentially. They can see how long is this computation taking, what are the memory accesses, and based off that, deduce what the underlying data is. And then finally, on the client side, we could have a rogue user, so not the trusted client, but somebody else who's sort of systematically querying the database system to deduce its private contents, right? You can send query after query after query to see if figure out the entire structure of the database. Okay, so let's look at what about existing work from the security and privacy community, right? Not the database community, but all of the fantastic work that has been done outside. And so that's true. There's some great work. However, a lot of these existing S&P solutions are piecemeal, or they focus on specific steps in a DBMS workflow because they weren't thinking about DBMSs from the start. So, for example, MPC and TEEs that we covered earlier in the tutorial. The idea here is that you protect data during computation. So while you're processing this information, you're not going to leak any private information. However, it doesn't really protect anything once that data is released. You could compute something, and then if the result of the query is some private information, and you release that, then you're violating or you're leaking this information, even if you weren't doing it during the computation. Second, with differential privacy, this sort of protects data when releasing results, right? So you can say, I computed some result and I want to release it to some untrusted party. You can use some differential private mechanism to do that. So, this seems like these two techniques can work well together, right? One protects during computation, one does it when releasing results. However, composing these techniques is actually non-trivial. Okay, and so that sounds great. So where do we come in as database researchers then? So today, database research, we mostly focus on making the database systems fast and scalable. It's a really great success. We have really fast systems now. We get answers as soon as we want. It's fantastic. And for us, typically, so security and privacy is usually an afterthought, right? It's like, oh, it's this thing I have to tack on top to make sure that I don't get sued, essentially. However, the argument we're making today in this tutorial is that we actually have a lot to offer in this emerging space of making privacy-preserving analytics practical and usable, right? So if we can make regular database systems fast and scalable, then we believe we can make private and secure database systems fast and scalable. Okay, and so to this end, we have come up with the idea of this trustworthy database management systems, right? And here we have a few things that we want to support. So first and most importantly, we want end-to-end security and privacy guarantees, right? We want to cover security and privacy from when a client submits a query all the way to when they receive the results. Second, we want efficiency. We want to have efficient performance. So we want to offer performance comparable to that of current DBMSs, right? It's unlikely to be just as fast as computing in the clear. We want something that's close enough to where people are willing to use it. Okay. Next, we want our systems to be robust, right? We want to support ad hoc query workloads and diverse user needs. We want to be able to support a wide range of applications, as wide as possible. And finally, we want our system to be useful, right? We want a UI that's like a standard DBMS that has a low barrier to entry. We want people to be able to understand our S&P security and privacy guarantees and be able to have confidence in what they're using. Okay, so the goals of our database system here is we want to have rigorous, explainable guarantees of privacy of storage, as well as computation over data. We want to have privacy for the data itself, especially under repeated querying. And then finally, we want to maximize our query result accuracy. And we also want to maximize the speed of our query execution. And the thing we need to notice here is that, and this is very important, is that security and privacy guarantees are not Boolean, right? There's not 1 or 0. It's not either secure or not, or accurate or not. There's actually, we can have some amount of accuracy or some amount of speed. And so this leads us to be able to make some really interesting trade-offs, right? Maybe we can sacrifice some accuracy to improve speed, or sacrifice some speed to improve privacy. And so we look at some systems later on that make this exact trade-off. But first, let's evaluate some existing approaches using our requirements here. And so first, we look at secure computation, right? This is our MPC and TEs. And these techniques protect data during query evaluation with a couple of things. First, data that's encrypted in flight, as well as oblivious data-independent execution transcript. And so this is really useful for query processing in an untrusted cloud, right? You can just upload some data to the cloud, and the cloud can carry out these MPC workload or using TEs to compute a securely and return a result. However, in this case, MPC is really, really slow. It can be up to 1,000 times slower than running in the clear. And TEs, on the other hand, which are much faster, however, they require specialized hardware and depends on sort of chip vendors to have corrective inflations, which at the moment, there's a sort of cat and mouse game between coming up with a new TE and then having people come in and break that implementation. Okay. And so the thing about MPC and TEs is they do not protect data during data release, right? So it's really only talking about during computation. And as such, if you repeatedly query an MPC or TE only system, you could leak information about what the private data distribution is. And, we want to say that revealing any data. So basically, we say that here that revealing any data-dependent computation, such as intermediate result sizes, will leak private information. And we can see an example of this in the figure on the bottom right here. So here we have a query tree that has some operators associated with it. And in the brackets, we're going to be showing what's the maximum size, output size of each of these operators. Okay, so we can see with the input tables, we're assuming those are all size n. We have a filter here, in the worst case scenario, the output of this could be size n. We have a join, the output of worst case size of this is n squared. The second join on top of that could be n cubed, and so on and so forth. So you can see this sort of exponential increase. And the reason we have to do this is because we have to, if we didn't do worst case scenario, then an attacker could look at the size of your intermediate results and deduce some information about the input data. Okay, and so this is why we require MPC and TEs, and one of the reasons why it's so slow. And so if we look at our requirements here on the top right, we can see that MPCs and TEs, secure computation allows us to have accurate results, just as accurate as sort of plain text execution. And it also gives us, great compute privacy, where we can protect data that's in flight by using this sort of oblivious execution. However, speed is lacking, so it's going to be much slower. And then also, it doesn't really protect anything query results when we're releasing data. So the data privacy is also lacking. Okay. So we can look at our second approach here as differential privacy. So differential privacy reveals statistics about database workloads, database records, while withholding information about individual input tuples, right? And so it does this by injecting precisely calibrated levels of noise into query answers that's proportional to individual contributions. This is composable, so we can use multiple GP mechanisms in conjunction with each other. And we have this sort of, it provides us a nice provable guarantees on information leakage. So we can bound cumulative information leakage subject to a privacy budget, referred to as epsilon. Okay. And so DP-only systems typically add noise either to the query result that's computed by a server or the input data from data owners. Okay. So if it's up on a server, then some server collects all its private data. So there's trust there that the server's allowed to look at them, look at the private records. They'll compute some result, add some noise, release the noisy result. Okay. And so that's great. So when we add noise to a query result, we have a single data owner. What's trusted, we can do this quite easily. However, when we think about multiple data owners, so for example, we have a bunch of smartphones. Each of them belong to some user who has some private data that's being uploaded to some server, untrusted server. To handle this, each individual client or data owner will be adding noise to their contribution to the result. And this leads to the situation where we have error that's proportional to the number of owners, right? So this introduces a lot of error into the system, which is not so great for accuracy. And so we can see here on our requirements or our metrics, we can see that accuracy here could be, depending on the implementation, can be lower than execution in the clear. Speed can be lowered as well because some of these mechanisms become very complex and require some overhead. But however, our data privacy is fantastic because we have these strong mathematical guarantees on information leakage. And then finally, we don't really consider, or we don't have much compute privacy in this setting with differential privacy because it does not sort of continue. It requires some trusted owner, either whether it's an individual client or an untrusted cloud server. Okay, so this leads to the idea is like, well, why can't we sort of naively integrate these building blocks into an existing system, right? And so here, have to take a look at our first problem here is we're going to be presenting. We want to prevent side channel attacks, right? So side channel attacks in terms of access pattern leakage or volume leakage or timing leakage. Okay. And so first one, access pattern leakage. This is when you have memory locations that are accessed during computation. And this can leak the frequency of values in source data. We could have volume leakage where we leak, this is basically leaking the size of our computed results. And so this leaks the number of records processed at each operator. Finally, we have time linkage. This leaks the time required for computation. And so this, meaning that the time needed to process output of each operator, right? And so if we have this information, we know the frequency of values in source data or the number of records processed at each operator or the time it takes, then this reveals some information. This is our side, all side channels that can reveal some information about the distribution values in the private source data. Okay, and this is what we want to avoid, this leakage. Second problem, we need to properly compose our techniques. So we have to combine secure computation with a DP mechanism and release to some client, right? And so if we naively did that, so okay, what if we just use secure computation or MPCs or TEs to do the computation? And then once we do the computation, we use differential privacy to then add noise and release this result. Right, and this gives us a result here on the bottom. We can see is actually this would give us sort of poor speed, poor accuracy, but in addition to our great compute privacy and data privacy, right? And so that's a problem for our database systems. We want it to have great performance, and we want it to have accurate results. And so next, we were going to go into is like how can we properly compose these techniques to achieve our goals. Okay, and so for this, we're going to look at some existing state-of-the-art solutions. So the first system we're going to be looking at is called Conclave, which is it's about secure multi-party computation on big data. And so this is actually going to be a system that's mostly focused on MPC, but however, it's going to be using some very interesting, very novel techniques of leveraging the database structure in order to improve MPC performance. Okay, and so what it does is basically it has a compiler for relational queries that accelerates secure computation. Right, so what this means is how it does this is instead of directly converting SQL queries into secure computation blindly, just taking the whole query and constructing an MPC program, what it does is it transforms these queries into combinations of small data parallel local clear text processing as well as small MPC steps. Right, so you can see here in the figures, instead of converting all of these operators into MPC, it takes portions and pieces of it. Can we do some small portions in MPC with the rest in clear text, only when necessary. So in this way, we're able to reduce the amount of MPC or secure computation necessary in order to drastically improve our performance. And so the great thing about the system here is that it's able to prevent side channel attacks, and it also improves speed through less MPC. However, it still does require some expensive MPC, and it only really, at the moment, considers protecting data during computation. And so if we evaluate on our metrics here, we can say, great accuracy, great compute privacy, speed is okay, but can be improved. And then finally, we don't really have any data privacy in this setting. Okay. Our second system that we're looking at is called Opaque. And this is an oblivious and encrypted distributed analytics platform. And so this is a distributed analytics platform built on Spark that utilizes TEE's secure enclaves for oblivious execution. And the way this is, it introduces oblivious relational operators for rule and cost-based query optimization with security and privacy guarantees, right? And so it has to sort of rewrite these operator implementations to support TEEs. However, in doing so, it's able to sort of, provide security and privacy for our query execution. And so this is great. Prevents side channel attacks and improves speed for TEEs. Downside here is it requires specialized hardware, and again, only protects data during computation. Right, and so for our metrics, great accuracy, speed is much improved, great compute accuracy, but again, does not really consider a data privacy or the privacy of the data that's released. Okay, so our third system we're looking at is called ShrinkWrap, which is secure query execution with DP guarantees. So for disclosure, I am the first author in this paper, so maybe a little bit biased. But so here we have some extended security and privacy guarantees with differential privacy. We're going to combine differential privacy with MPC. And we want to cover, sort of prior knowledge of data owners with respect to query answers, cumulative privacy loss from repeated querying, as well as collusion among data owners and the client. And so the way we do this is we reveal noisy intermediate cardinalities at runtime for speed up. So instead of doing worst case cardinalities every single time at every output of every operator, we're going to be using differential privacy to create noisy versions that are smaller. Okay, and in addition, we noise query result answers in MPC at the end, such that the true answer is never revealed. Only noisy result is revealed. Okay, so we can see here in the red, you can see the worst case oblivious execution sizes, and in the blue, in the brackets, we can see a noisy intermediate cardinalities. Okay, and so great things about the system: it prevents side channel attacks and improves speed through TP volume. However, it does still require user-defined trade-offs. So the user will be in charge of figuring out, how do we set epsilon, how do we apply differential privacy, what is needed, and also there are limits on repeated querying because it uses a privacy budget from differential privacy. You can only query so often without until your privacy budget is totally consumed. And so you can see in terms of our metrics, we can see accuracy is all right, pretty good. Speed is also pretty good, not as good as clear text. Our data privacy does well because we have differential privacy to provide our guarantees. And finally, compute privacy also does all right because of we're using secure computation here. So you can see here, in this system, it's the first system that is able to achieve good ratings at least in all of our metrics, even though it's not the best in any of them. Okay. And then the next system that we're looking at is what's called cryptD. So this is crypto-assisted system that combines MPC with DP to execute database queries over data that's collected from multiple data owners. Okay, this achieves a strong accuracy guarantees without requiring data owners to upload private data to some central trusted data collector. Okay, and so here we have a way of converting local differential privacy where we have individual users adding noise to each one, where we have an error that's proportional to the number of users, into something like central differential privacy, where we have a single owner that adds noise once. Okay, so to reduce the amount of error. And so to do this, it uses MPC to serve as this sort of trusted server without actually requiring a trusted server. Okay, and so great thing here is that it can ensure privacy through differential privacy and improves accuracy through using MPC. Downside here, it still does require some expensive MPC computation and only supports linear aggregate queries. So again, similar to shrink wrap, the system is able to achieve some amount of accuracy, speed, data privacy, and compute privacy, depending on the settings that the user selects. Okay. And so those are kind of the main state-of-the-art systems that we have. There's many more. Again, this is a very non-exhaustive list. And I can encourage you to reach out or to ask questions about other existing systems that do a fantastic job as well. Okay, so the final part of our module today is going to be our open challenges. So there's some exciting research work or ideas that can come out, and then we're really excited to see how other people tackle these challenges. So first, we're thinking about is growing databases. So all the databases we sort of discussed before sort of mostly consider the static setting, where the data is set once, and then we have some system that runs on top of that. So when we have a growing database, right, this is where records are constantly coming in, and the data is not static anymore. And so in this setting, we have an additional leakage, which is called update pattern leakage, right? So the update pattern, or how often the timing of these updates, actually reveals some information about the source data, which could sort of violate our privacy guarantees or result in privacy breaches. And so this requires some further countermeasures that hides update patterns. And I believe there's actually a paper here in Sigma 2021 called DP Sync that sort of handles this update pattern leakage. And so for an example of a real world privacy leakage from growing database, you have some secure outsourced database. You have two IoT sensors. You have a person, right? So the person walks through, they go through one IoT sensor, and this sensor will then sort of back up an encrypted IoT event. A person goes to a second IoT sensor, and again, the sensor backs up some encrypted IoT event. And we can see that based on when these sensors update, the update pattern of these sensors, or when these updates happen, you can determine, what was the path that this person took, right? And so you can see floor by floor is like, okay, these sensors were tripped, therefore this person, based on these updates, this person took this path to these floors. Okay, and you can use the sort of average walking times or something to induce this. Okay. Yeah, and so with that, you're able to learn the location that this person went to, which is a privacy breach. And so this is because the event time is strongly tied with the backup time, right? This is called a database update time. And an adversary can breach this privacy by using the time information of updates. And this type of attack generalizes to any event-driven update where the event time is tied to the data upload time. And so the challenge here is like, how can we decouple this event time from the upload time while sort of preventing, while still achieving, timely information? And it's just the Sigma, again, this is the paper DP Sync that's in the conference. Again, this full disclosure, I'm an author on this as well. but I encourage you to seek this out. And finally, with some additional challenges, right? We have to think about transactions. If we have asset transactions, how does this work in a security and privacy setting? Second, how about floating point support? How do we do this? In differential privacy, there are a lot of leakages that are attacks based on floating point. How can we sort of handle this in a database setting? And finally, we have query interfaces. So we have these additional security and privacy parameters. How do we present this to users? How are they able to sort of either set it or find it automatically set? And as well as how do they even understand what this means? What does privacy leakage mean to them? How, if our accuracy, how can we provide sort of confidence intervals on our accuracy, or give them any sort of intuition about this through the interface? And finally, just to conclude, there are three main topics that we talked about today. We're looking at, sort of security and privacy require advanced techniques beyond just sort of simple passwords. We have, existing solutions that blend techniques such as MPC and DP to negotiate trade-offs. And finally, there are many open challenges that exist that require additional research work. So hopefully through this module today, you learned something about sort of system implementation and optimization, and we're happy to answer questions. So either feel free to reach out, ask questions now, or to email us or seek us out. So again, thank you so much for your attention, and looking forward to seeing you in the next module. Great, yeah, thanks again for listening, everybody. And please, if you have any questions, either write in the chat, speak directly, or feel free to post it on Whova or office hours. Cool. Well, yeah, if we don't have any questions at the moment, again, feel free to, either in the next session or sort of offline, feel free to ask, and we'll be happy to answer everything. And yeah, I guess I don't believe there's any additional modules that we need to discuss, unless we have a conclusion.
Excuse me.
Oh, sorry.
Can I ask a question?
Yes.
Yeah, I come again. Thanks a lot to give a wonderful talk. And my question is, from your talk, I know currently the DP mechanism for DBMS has already support many queries like join operation and the aggregate, right? But I wonder, is there any work to support more complex queries like min-max query and some query involving the selection condition? Of course, the selection condition refers to the ones involving multiple relations. I mean, the selection condition involving single relation is very simple because we can solve it in a pre-processing stage. Yes. So is there any idea to support such more complex queries?
Yeah, that's a great question. So yeah, just to reiterate your question to that, you're asking about in these sort of like DP sort of MPC systems, there has been a work with like sort of supporting join queries or aggregate queries, but is there additional support for more complex queries like min-max or selection? Is that correct? So yeah, so that's a good point. I think there are systems in terms of if we're thinking about combining DP and MPC, and so that'll require us to sort of implement, these more complex within MPC, right? And so, because we want to be able to do those in MPC and then sort of add noise to it on top of it. And so they are possible. I think there are some like sort of specific purpose-built systems that, sort of one-offs, but I don't think there's like a single system that incorporates all of them at the moment. But it's definitely a great sort of open question for future research. I'm sure, Xi and Xiao, if you have any additional input on systems that you see with that, feel free to chime in.
Okay, I see. Thank you.
Yeah, thanks again for a great question. Yeah.
Thank you.
Yeah, so just to add up on that, for some of their aggregates, for example, min max, right, their sensitivity for those aggregates is really high. So there's no guarantee, accuracy guarantee for them if you want to achieve differential privacy. Yeah, and also for selection in the more complex joint queries, and actually, yes, they're actually, for example, I think privacy code can handle selection operators even before the join queries. So we apply a query, a set of rules to analyze the sensitivity of a more complex query plan. So it's doable in privacy code. Okay, that's wonderful. And I think there's also a lot of new operators need to be building in MPC settings as well. So I think the set of tools that shared by Shao is really wonderful. I think it definitely worth their investigation, exploration.
Yep. So mostly like from the MPC perspective, the feasibility issue has been solved. We know that everything can be computed, but like there's not really anything. There's not much we can see in terms of the efficiency. I mean, like so they are like most of the systems are built not for like database operations. So the like there's going to be a lot of work that is needed to kind of to efficiently support all the like database operations efficiently. For example, I think there will be a session in this Beijing time afternoon. Like there will be like there are some papers about it.
Sounds great. Great. I hope you all have a great time